To talk about similar matrices, I first want to motivate it with an example that we've already seen how to do. So I want to first take this function f from R3 to R3, and this function is given by the following. F of xyz, this vector, is equal to this matrix, which is 0, 1, 2, 3, 0, 0, 3, 0, 0, 0, times the vector xyz. So we are taking a vector and saying f of a vector is equal to this matrix here times vector. Anytime that you have that situation, I said this in a previous video, I'll say it again. Anytime that you have f of a vector is equal to matrix times vector, then the representation of that map f with respect to the standard bases for the domain and codomain, which in this case are of course equal, the representation of f with respect to the standard bases is the matrix that you were just multiplying by. Okay, so here's a different basis. B is equal to the basis consisting of the vectors 2, 0, 0, 1, 2, 0, and 1, 0, 1. So what is the representation of f with respect to B and itself? So we've seen examples like this before. The best thing that we can do to figure this out is well, I like to start it with this diagram here. So we have let's call this matrix M, and so we're looking for basically this part of the diagram here. So we have the function f is represented with respect to B in the domain and also B in the codomain. So here it's important that the domain and codomain are the same and that the basis is the same for each of those. So anyway, M is our representation for this first part of that diagram. And A, let's see, did I call this A up here? No, I should call this A. Let's call this guy A. That is our representation of our function f with respect to the standard bases. And here I have so I'm calling this matrix representation P. And so this is a change of basis matrix. So P is a change of basis matrix from R3 to itself with respect to B and the standard basis. So I'll say the representation of the identity with respect to B and E3 of the identity. And then if I do that, then over here on the right column, it's just the reverse of the arrow from the first column. So I just basically am reversing the arrow because here I have B to E3 and here I have E3 to B, just going up instead. So that's the identity. And since I'm just reversing the arrows, then this in this case turns out to just be the inverse of this matrix P over here. So I just need to figure out what P is to start this problem off, and then I can find P inverse. Or I could find P inverse and then I could find P by taking the inverse of P inverse. So whatever one seems easier, I'll go with that. And so which one should be easier? Should the representation of the identity with respect to B and E3 be easier, or the representation with respect to E3 and B? Which one should be easier? And as we've talked about in previous videos, the answer is almost always, probably always, going to be the one where the standard basis is the second one here. Because if this is our basis right here, then P, and since I've already gone through an example like this, I'm just going to go through this a little bit quicker. P is just going to be obtained by taking these basis vectors up here and just putting them into a matrix. It just works out that nicely that that's how you find this representation. So anyway, so next thing we have to do is find the inverse of this matrix, and then the upshot of that is that, so we're looking for M, right? So if we're looking for M, then we can instead just go around this diagram. So we first, so M represents F by saying, well, if you take a representation with respect to B and then multiply that representation by M, you get a representation with respect to B of F of that vector. And so I can instead multiply that representation by P, and then on the left again by A, and then on the left again by P inverse. And again, so we're reading right to left there, so M would be equal to, well, let me read it from right to left. So I do P first, and then I do A, and then I do P inverse. So M is equal to P inverse AP. So all we have to do, so we already know what A is, and we already know what P is. We just need to find P inverse, and that's just a matrix inverse calculation. And we've already seen how to do that. I copied and pasted it over into this because I didn't want to go through the calculation, but I'm going to leave it on the screen in case you want to check that this is correct. But anyway, just to remind you, the process is we put our matrix P side by side with the 3 by 3 identity matrix, and we do row operations that take P to the identity matrix, and then we do the same row operations to the identity, and we get some matrix at the end here, which looks like this, and that is our P inverse. So P inverse is equal to, I'm just going to factor out a fourth from everything. So this would be 2, negative 1, negative 2. This would be 2, this would be 4. Hopefully that's right. So that's our P inverse. And let's maybe bring down our matrix P. So here is our matrix P. And what was our matrix A? Let's bring that down as well. So here's our matrix A. And we also said that M is equal to P inverse AP. Which is equal to 1/4 times 2, negative 1, 2, 2, 0, 4 times A knit times P. Okay, let's just multiply this out, see what we get. Let's multiply the first two together first. Okay, what do we get? I get 0. So, okay, so the entire first column here is a column of 0. So when I do like first row times first column, second row times first column, third row times first column, those are all just going to be zeros. So that makes this a little bit easier. If I do first row times second column, I should get 2 times 1 plus 0 plus 0. And then I'll get 0, 0, 0 right below it, and then I'll get zeros again right below that. Yep. Okay. What about the top right entry? I get 4 minus 3 plus 0. 4 minus 3, that's just 1. And then I get 0, 6, 0. And then this last one should be a 0 as well. 0, 0, 0. Yep, that's a 0. Okay. And then 2, 1, 1, 2, 0, 1, 0, 0, 0. And then we'll be done after this. 1/4. Okay. First row times first column, zeros. Yep, that's a 0. First row times second column, 0, 4, 0. First times third column, 0 plus 0 plus 1. Second row times first column is 0 plus 0 plus 0. 0 plus 0 plus 0 again. Is that right? Yeah. And then 0 plus 0, 0 plus 0 plus 6. Should get a 6 right there. And I think the last row is just going to be a row of zeros. And yeah, so I'm multiplying row 1 times columns 1, 2, and 3. And since row 1 is just a row of zeros, then that's what we get. So this is equal to the representation of f with respect to our new bases, b in itself. I could distribute this this 1/4 at the end too. It doesn't really matter. Maybe I'll just do that real quick. So this would be a 1. This would be a 1/4. And this was a 6 before. Now it's 6 over 2, which is 3/2. Okay. Right. So yeah, that's it. So keep in mind, how do we construct this? So we're specifically using R3 in all 4 of those corners in that diagram, right? And in the bottom, let me go back to the diagram. In the bottom half of the diagram, I have the standard bases. It doesn't actually matter that they're the standard bases. It just matters that this basis and this basis are the same. And then the same for the top. This basis and this basis are the same. I have B and B both being used for the top left and top right. Okay. And so as long as I do this, then I get that M and A are an example of similar matrices. So M is equal to P inverse AP. This is an example of matrices being similar. Okay. So note that A and M, which is equal to P inverse AP, they both represent the same map with respect to different bases. A for the standard bases and M for the basis B that we constructed. Or were just handed, rather. So yeah, A and M are an example of similar matrices. And here's our definition. Matrices A and B are similar if there is a non-singular matrix P, so an invertible matrix P, such that A is equal to P times B times P inverse. It didn't matter whether you had the inverse over there or over here. I'm just going to put it over there because it doesn't matter, because as long as there is some non-singular matrix such that you can do this whole thing, then the definition works just fine. So anyway, that's our definition. That's our working definition. Let me do one more example. This is just to construct an easy example of similar matrices. So here's a matrix A, 1, 2, 1, 3, and here is a matrix P, 1, 3, 2, 4. P is a non-singular matrix. Its determinant is 4 minus 6, which is negative 2. And so its inverse is 1 divided by negative 2, multiplied by the matrix. So you switch the diagonals and make the off diagonals negative. So 4, negative 3, 2, 1. That's our P inverse. And so let's construct a matrix that is similar to A. And so we could just do PA, P inverse. We could have also done P inverse AP. That would be a different matrix. That would be similar to A. But we'll just do PA, P inverse. So P times A Okay, times P inverse, which is, I'm just going to distribute the negative a half. 2, 3 halves, negative 1 half, and then positive 1. This is equal to, I'll multiply the first two together first. So I get 1 plus 3 is 4. 2 plus 9 is 11. 2 plus 4, 6. 4 plus 12, 16. That's being multiplied by negative 2, 3 halves, 1, negative 1 half. This is equal to negative 8 plus 11. That's equal to 3. First row on second column, that's 4 times 1.5 is equal to 6. Plus 6 minus 11 over 2. I'm just going to simplify later. And then second column, what do I get? Negative 12 plus 16. Negative 12 plus 16 is 4. And then bottom right, I'll get 3 halves times 6. That is equal to 9. 9 plus 16 times negative a half, that's equal to negative 8. Great, so this is equal to what? This is equal to 3, 4, 11 halves is 5.5, so this would just be a half, and this is just a 1. Okay, and so this matrix